Okay, folks, so I've put up mark schemes for the questions that we are catching up on to this post, so they will be there. So if there are any issues with them, please come back to me. Please remember to have your 2021 head on it, not your 2010 head. This, I think, is around page 97. I will double check. We're going to start there. So these are the graphs that we would have drawn from the data we collected on Friday and on Monday. So we have page 96, 97, we'll have these graphs, and page 91, 92. So it can either be temperature or concentration on your axes, and the trend is the time to react decreases as your concentration increases. Similarly, if it's temperature. And when we do rate as a function of concentration or temperature, we get this linear relationship. You can see from your data that it might not be exactly linear. And we describe this line by saying rate is directly proportional to concentration or to temperature. If you do chemistry in third level, you will do kinetics, and at this point they start talking about the orders of your rate of reaction. But we don't touch it at leaving cert. So there would be new stuff to learn there. So that applies to both the concentration graphs and the temperature graphs that we drew. I am looking now at the bottom of page 92 underneath our rate as a function of concentration graph. And we know from our experiment that the higher the concentration of reactants, the higher the rate of reaction. You have to fill the gap now with our collision theory blurb. So essentially we're looking at that more particles are going to be present. We have a better chance of these successful effective collisions in the correct orientation and in the production of product. So there will probably be a marking point for the first, that will be one marking point, and then it will be something from this internal bit on collision theory. So please make sure you are happy with that. The other thing that we're going to put in is when we did our, if we look at production of a product, the graph has a very particular shape, and if you have to be able to explain it, so this is the particular shape that we're looking at, if you have to be able to explain it, it's what's going on. So we have this sharp slope over here because we have loads of reactant present, so they're doing their successful effective collisions, correct orientation, making loads of products. And our slope gets less steep as we move up because there's less and less reactant until finally it levels off because we have used up either one or both or all of our reactants. So I would like you to put just the shape of the graph into your gap on page 92, and these are the words that we're interested that explain it. So over time, we are saying the concentration of reactant decreases, our rate of reaction decreases, and the slope of our graph decreases over time, and that is due to product being made. Just to remind you at this point, if you are doing a question and they've given you product and they've given you time and they might tell you I have 50 centimeters cubed of 1 molar X, and they will ask you to, what would the curve look like if I had 50 centimeters cubed of 5 molar X? And they want you to recognize that this slope would have to be sharper because it's 5 molar now, it will have to end higher. So the volumes will be the same, but the difference in it will be the concentrations. And that they'd ask you to, draw on your graph to show. So please recognize that if you've got a higher concentration, it's going to be a faster rate and it's going to end higher up because you're going to make more product for yourself. Alrighty, so that brings us to the end of concentration and temperature, their effect. And we're now going to have a look at catalysts and see can we understand a little. Okay, so we are now, at least I am on page 104, and what we're going to talk about now is the effect of a catalyst on the rate of reaction. So we know already that if we add a catalyst, it's going to increase our rate. So we do know that piece of information already, and now from this we're just going to get a better understanding as to how it's going to do that. So we need to take into account when we talk about effects of temperature and effect of catalyst, we have to take activation energy into account. So you're going to pause now and you're going to draw energy profile diagrams for exo and endo, and you're going to label them with activation energy and with your delta H. Please make sure you can do that, so pause now. So this is our energy profile diagram for an exothermic reaction. Exothermic reaction gives off heat, and it has a delta H value which is negative. That tells you it's exo, and I've asked you to remember that if we say the reactant has 0 enthalpy, because the products are lower, it's going to be in the negative range. When we label this up, we go from here to here is our activation energy. So the activation energy is the minimum amount of energy a particle has to have so that it can go through successful effective collisions and make product. So think of it as a hill that all of your particles have to get over before they can actually react to make product. And down here is our delta H value for our enthalpy to prove it's exothermic. Okay, so similarly down here for endothermic. Endothermic absorbs heat, so our enthalpy value is always positive. And again, imagine this is a 0, we're now in the positive range, so our delta H value for an endothermic is always positive. In terms of our labeling, we still have this big hump to get over in terms of activation energy. So that still exists. And down here, from this level to this level, this would be our delta H value. So that's just a little bit of revision from Form 5 and from junior cycle because it's on yours. We're now going to look at what's called a Maxwell-Boltzmann energy distribution curve. We have already seen these two gentlemen when we did the kinetic theory of gases. So these are the guys that came along and said gas molecules move in continuous random motion. They said that the volume is negligible. They've said there's no intermolecular forces. Collisions are perfectly elastic for an ideal gas. And obviously we know then that for real gases, it's different. Volume is not negligible. There are intermolecular forces involved, but these were these gentlemen. I just need to check that I'm locked. So we are going to draw a curve and we're going to explain it. Actually, no, I lie. We are going to look about how to draw on an energy distribution curve. So the first thing that we're going to say is there are no particles when we draw this curve that have 0 energy. So all particles will have some particles will have a really small bit of energy. So there's none, so that means we're not going to be starting right here at where the 0, 0 would be. There are going to be a distribution of particles that have higher energy. And there's going to be a peak, and that peak is the most probable energy. So the vast majority of our particles will have this amount of energy when we draw our peak. And then we're also going to have a very small number of particles that have really, really high energy. So could you think now, what might that, have a little scribble and see what if you were drawing a curve for that. So no particles have 0 energy. There are particles that have higher energy. There is a peak, and there are a small number of particles that will have very high energy. What would that curve look like? So the area under the curve when we draw it will show us the total number of particles for the system we're looking at. And we are going to be putting in activation energy into our curves. We will come back to that one. So if we're drawing our Maxwell-Boltzmann energy distribution curve, what does it look like? So we've said there are no particles will have 0 energy, so it's going to start up high like this. We're going to peak, we're going to come down, and then we've said there are no particles, there's a small number of particles that have very high energy. So what's really important here is that it is not starting at 0, 0. There are particles that have energy, so it's not starting from this line and away we go. We've said our peak is the the peak is the most probable energy. So the vast majority of particles will have this amount of energy. We've said the area under the curve is the total number of particles. So that's AUC, area under curve. And we're going to put in our activation energy. So I'm going to put in my activation energy as being here. So we've said activation energy is the minimum energy a particle has to have so that it can collide in the correct orientation in a successful, effective way to make particles or to make product. So our activation energy is fixed. So in this scenario, the particles that are down here, these are the only ones that have enough energy for collisions. So the particles that are here, these are the only ones that okay, so they're the only ones. The rest of them are going to bump off each other, and it doesn't matter if they're in the correct orientation, there's just not going to be enough energy. They're not going to have enough to actually make product. So activation energy is a fixed value, and particles either have enough energy or energy greater than it, or they don't. Your activation energy is fixed. It is not going to change as we go through this. So down here for our activation energy, we're going to say only particles with energy greater than EA, because I'm just going to shortcut it because I don't have room, will make product. Okay, now we have to consider a scenario. If we now increase the temperature of this system, what is going to happen to it? So I'm going to change the color of my pen. So we're going to increase our temperature. What happens is we now suddenly get more particles that have more energy. So we're still going to have a small number of particles that are going to have very high energy. And now we can see from this scenario that suddenly we now have all of these particles that have way more energy, so we're now going to get more product. So this is a higher temperature. The red here is a low temperature. And you can see if we increase the temperature, we get more particles have more energy. That makes sense. We already knew that from junior cycle. But now the fact that they have more energy greater than your activation energy means you're now going to get a faster rate of reaction. Okay, so if the temperature is increased, the curve becomes slightly flatter and it's going to shift to the right. And more particles have energy greater than your activation energy. And that is why then our rate of reaction is going to increase. Okay, so I hope now you're happy with that and you can see it, from our curve. We increased the temperature, we gave particles have more energy than they had, and there are more particles that have energy greater than our activation energy. So this is really important to note. Activation energy doesn't change with increase in temperature. Just the number of particles with energy greater than your activation energy change. That increases. So the value of activation energy doesn't change. It's just the number of particles that have energy greater than it that increases. So you'll see there's some questions and that's the answer that they're looking for, the way they describe it. Because most people assume increase my temperature, increase my activation energy. No, it is a fixed value. Alrighty, so here we are going to go back and draw our original curve. So some particles there are 0 particles with 0 energy. We draw our little woo, and then it levels off like this. And I've done that possibly badly. So we have said that there are some particles that have very high energy. We have said this may be where our activation energy is for our reaction. And now we have to think about what happens when a catalyst is added. So we know catalyst increases the rate of reaction, but in reality what a catalyst does is it provides a pathway that has a lower activation energy. So the value that they have to actually hit is now less. So in our original scenario, no catalyst. These particles are the ones that are going to make product. So these have enough energy to make our product. But as soon as we put in a catalyst now, we've shifted the activation energy over, and now we get all of these. Everything here now has energy greater. So the advantages of putting in a catalyst is that more particles will have energy greater than your activation. As catalysts lower the activation energy. And thereby increasing the rate. Okay. So, junior cycle, you would have had the definition of a catalyst being something that speeds up a chemical reaction without being used up. So now we just have to leaving cert proof it. So it is a chemical that speeds up the rate of reaction. But now we can get fancy. It does it by providing an alternate or a different pathway. And we're going to do catalysis on Wednesday. So this pathway that has a lower activation energy. And thus it's going to increase our rate of reaction. So this is our leaving cert proof now. It's an alternative pathway that has a lower activation energy. So more particles will have energy greater than your activation energy, can successfully and effectively collide in the correct orientation to make us product. So just the last little thing that we're going to do is what happens to an energy profile diagram when we put in a catalyst. So if this is going to be our exo over here, and this would be the shape of our curves normally, and we do our labels. This is my activation energy is going to be in red. I'll make my enthalpy in blue. So that's my delta H is going to be in blue, and obviously in this scenario it's negative because it's exo. This is my reactant over here. This is my product. So what happens when we put in a catalyst? So no, I don't want it that thick. Is it not going to let me make it skinnier? No, so we won't use this. So I'm going to use blue dashes. So if I put in a catalyst now, what happens is the size of the hump actually decreases. So this is now my activation energy with my catalyst. So the hump gets much smaller. More particles have the energy, you're going to make your product faster. End of story. So similarly here for endo, that is uncatalyzed reactant product. This is my activation energy. This is my enthalpy. So over here, my delta H is equal to positive. If we put in a catalyst now here for this, we have just said the size of the little hill gets much smaller. So my EA cat is smaller. I have more particles that have energy greater than my activation energy. Therefore, I will make my product quicker. Okay, so that was exo and this is endo. So the hump is smaller. So they can ask you to draw an energy profile diagram and then draw it with your catalyst. What happens to it when there's a catalyst present. So the last little bits about this. So we know from junior cycle, catalysts are unchanged at the end of the reaction. They will be specific for our reaction. They technically only need to be present in small amounts. And this is our next topic, but they don't affect the position of equilibrium. So this will make sense when we get to the end of our next topic. Now, catalysts can be destroyed by things called catalyst poisons, or catalytic poisons, however you want to say it. And what these do is, we've said catalysts provide a surface. So catalytic poisons, they will preferentially, so they will get to the surface before your reactant. So the way we describe them is they preferentially adsorb. So please note it's a D, not a B, and preferentially means they take the place on this surface before anything else. So they preferentially absorb to the surface, and effectively they block reactants. So we have already done fuel. So our example from fuel was lead destroyed catalytic converters, and we'll talk about that on Wednesday's lesson as well. So lead is a catalytic poison, and you should be able to answer this. Biological catalysts. Enzymes are biological catalysts. Alrighty, so we've got one more thing to do. We're going to explain the effect of a catalyst on the rate of reaction, and we're going to use our collision theory blurb and what to do it. So, adding a catalyst so we'll think about what it is we do know. So adding a catalyst increases the rate of reaction, so we know that. We now have to do our collision theory blurb in the middle. So it's lowering the activation energy. So more particles have energy greater than your activation energy. So increasing chance of successful effective collisions in correct orientation, thus increasing your rate of reaction. Okay, so as I've said, the first and the last points are things we should have known before we ever started rates, and this is now our collision theory in the middle to explain. So I hope you get that. There are 2 questions to try for homework. One of them is in your hot pink book. Any issues, please get in touch.